Hello and welcome back to this course, covering the exam topics for the JNCIS ENT certification. In this section of the course, we're reviewing Layer 2 security and loop prevention. In this lesson, we'll be covering the theory and configuration of BPDU protection, loop protection, and root protection. So far in this section of the course, we've reviewed in detail how we can ensure we have a loop-free switching topology. This is ensured through the use of spanning tree protocol and its descendants, the rapid spanning tree protocol. This is a very important function because the forwarding loops are very bad for switches and generally all devices on the network. Spanning tree protocol, albeit slow, is a necessary evil within our switched networks. Even if to just protect against human error if we connect the wrong cable in the wiring closet, to make sure we don't accidentally bring down most of the network with a broadcast storm. Spanning tree protocol, however, does not have any authentication capability and inherently trusts what neighboring switches claim. If a switch comes online in the network and claims to have the lowest bid, all other switches will believe it without question and reconverge with that new switch as the root of the spanning tree topology. This, along with other significant effects that can be caused by human error or malicious actors, are what these three complementary features to STP and RSTP try to mitigate. So let's jump on in. First, let's just consider some of the situations that can occur where STP and RSTP could cause undesirable effects or even be exploited. Since RSTP and STP do not have any authentication mechanisms built in, the protocols simply believe whatever the other switches on the network tell them. This opens up the possibility for a rogue switch to be connected to the network. A rogue switch is one that is not expected to be on the network. Without careful configuration, the rogue switch could claim itself as the root bridge and cause an impactful spanning tree convergence event in the network. Let's say we have Bob and Allison. Allison's desk was recently moved here next to Bob, though there's only a single data jack in the area. Allison was instructed to just use the company Wi Fi, though the signal where she's seated is very poor and she's being dropped from Zoom calls very often. Bob notices Allison's struggle. He's all too familiar with the fury that can build from constantly playing the "Can you hear me now" game on an important meeting. Bob brings in an old desktop switch from home he had replaced a couple years ago to help alleviate Allison's pain and provide her a wired connection. This was done with the best of intentions, of simply helping his fellow coworker to be more productive and to hopefully eliminate some pain and suffering from the world. Many of these consumer grade desktop switches do not participate in STP or RSTP. However, when Bob purchased this switch, he got a top of the line switch, thinking it would benefit his home network. This switch came with all the bells and whistles, including the ability to run spanning tree protocol. Being that the desktop switch is quite old, the MAC address assigned is very low since the manufacturer allocates MAC addresses sequentially. And since the network administrator has never configured the bridge priority of the core switch in the network, as soon as the new switch is plugged in, it flooded superior BPDUs into the network and was elected the root bridge. Bob and Allison didn't notice that several other people in their office area had their Zoom meetings drop almost immediately after plugging in the switch. But everything came back up in less than a minute, so IT was never made aware of the brief outage. Since then, however, that floor has been plagued by network performance troubles and periodic outages, as the poor little consumer grade desktop switch, which hasn't gotten a software update since its creation, is trying to cope with the network traffic of an entire floor of a business office. As a network administrator, this is a pretty difficult situation to locate and resolve without intentionally looking for it. Many hours will be wasted troubleshooting the network, and potentially money wasted replacing various pieces of equipment in an effort to alleviate the chronic network troubles. You can probably tell this is not an optimal situation, and leaving the fate of your network up to the whims of the employees plugging anything into a network jack is just not good practice. In this situation, Bob and Allison accidentally caused a lot of mayhem. What if someone actually knew what they were doing and were intentionally trying to become the root bridge to snoop on the transit traffic? It doesn't even need to be end users and malicious actors causing the trouble. We, as the network administrators, can even accidentally wreak this kind of havoc ourselves. We've all been there before. We have several competing priorities, or we've been handling an outage for the last 8 hours, and you need to put a new switch into place. So you give it a bare bones configuration and plug it in, only to find out later that there's new network issues and performance troubles that you're not sure are even linked to the switch you installed, or might be something new, on what seems to be an increasingly unreliable network. Making a little mistake can cause significant issues in networking. So, why not put protections in place to save ourselves from these mistakes, or from end users, or help protect us from malicious actors? That's what the three technologies we'll review in the upcoming slides will help us with. So, first, let's take a look at BPDU protection. BPDU protection is a feature that will place a port into a blocking state if a BPDU is received. As you can probably tell, this should only be configured on ports which are expected to never connect to another switch or receive a BPDU. You may recall the edge port role in RSTP, which is an excellent feature for ensuring interfaces connected to end hosts come up and pass traffic as quickly as possible. Being that these interfaces are connected to end hosts, we would not expect to ever see a BPDU received on one of these ports. Unless, of course, we have a situation like Bob and Allison, and an unexpected rogue switch is plugged into the network. However, in RSTP, if an edge port receives a BPDU, the port will simply start participating in the RSTP topology, unless BPDU protection is configured. If you're coming from a Cisco background, this feature is much like BPDU guard seen on Cisco devices. As our topology shows, the feature will block ingress BPDUs from being processed and will place the port into a blocking state if one is received. These BPDUs would be sourcing from another switch. Or, if a loop is formed accidentally, then they could be originating from the local switch too. Let's take a look at how we configure BPDU protection. BPDU protection is configured at the Edit Protocol's Layer 2 Control configuration hierarchy, where member interfaces are added under the BPDU block command. BPDU protection may be configured whether the switch participates in spanning tree or not. You may have a use case where you want to block all BPDUs received on a switch which doesn't participate in spanning tree protocol. The feature may also be configured under the Edit Protocols RSTP configuration hierarchy. Applying the BPDU block on edge command will enable BPDU protection on all edge roll ports in RSTP automatically, which is a common method of implementation. Now that we know how to configure BPDU protection, let's review the next feature, root protection. Root protection is used when we have a purposefully designed and deterministic switching topology. This feature will place a configured port in a blocking state if a superior BPDU is received on that port. As you can imagine, this feature should only be configured on ports which are expected to never become root ports. In our three-tier hierarchical campus network design, this would be configured on the downstream ports at the aggregation and perhaps even core layer. This would ensure that nothing at the access layer may impact the spanning tree topology at the aggregation or core layer if a misconfiguration occurs. By default, once the superior BPDUs are no longer received, the port will automatically revert to the forwarding state. So let's see how we configure root protection. Root protection is configured under the Edit Protocols RSTP configuration hierarchy, under individual interfaces with the No Root Port command. It should be noted that we cannot configure root protection and loop protection at the same time on the same interface, only one or the other. If you attempt to configure both at the same time, you'll simply receive a commit checkout failure when attempting to commit the configuration. That leads us into the final feature we'll cover in this lesson, loop protection. This feature protects against a somewhat specific set of circumstances. So let's first take a look at an example scenario. In some situations, such as a software bug or failure, or a particular type of link failure, a port can become unidirectional. It may still be able to transmit but not receive traffic, or the other way around. Either way, this can cause serious trouble with spanning tree. This type of failure is more common with duplex fiber optic links, in which separate physical fiber optics are used for transmit and receive, or ingress and egress. If one of the two fibers becomes damaged or cut, it's possible the link will remain up and become unidirectional in nature. In the topology shown here, the link between switch 2 and switch 3 has become damaged, such that switch 3 is no longer able to receive traffic from switch 2, but switch 2 is still receiving data from switch 3. Since we are running RSTP and BPDUs act as a keep alive mechanism, once switch 3 doesn't see a BPDU from switch 2 for 6 seconds by default, it will assume there's an issue and proceed to transition this port from an alternate to a designated port in a forwarding state, which will then create a forwarding loop. Although unidirectional links are somewhat rare, we cannot allow this situation to bring down the entire network. So, how exactly does loop protection save us from this situation? Loop protection will not allow a blocking or discarding state port to transition to forwarding if BPDUs are no longer received. What we'd expect in RSTP, if switch 2 were cut off from the root, is to see superior BPDUs ingress at switch 3. Ceasing to receive BPDUs entirely while the link remains up means that switch 2 has either had a software failure causing the RSTP or STP process to misbehave, or the link has become unidirectional. Both situations are bad, and should not result in the port on switch 3 transitioning to a forwarding state. Loop protection will transition the port into a loop inconsistent state if BPDUs are no longer received while the port remains up. This should be configured on all non-designated ports to ensure loops are not formed. So let's see how we enable loop protection. Similar to the other features we've covered, loop protection is configured under the Edit Protocols RSTP configuration hierarchy, using the BPDU timeout action command under the participating interfaces configuration. As we can see here, there are two possible configured actions on BPDU timeout: alarm or block. The alarm action will create a log message, but will not actually block or transition the port to a loop inconsistent state. The block action, however, will take the corrective action, and this must be configured under each interface individually. Once we configure and have loop protection in our network, how will we know, beyond taking a look at the logs, that the port is in a loop inconsistent state? As we see here in the output of show spanning tree interface, a port which has triggered loop protection will transition to the discarding state with the loop prevention marker. This will only occur if we have the block action configured. If the alarm action is configured instead, we'll only see a log message, similar to the one shown here, with a loop protect syslog. Thank you so much for working through these three very important layer 2 loop prevention and security features with me. I hope that this lesson has been informative for you, and I would like to thank you for viewing.